in one of our previous meetings, we placed the structure, or we derived the structure of the key equations that we need to understand steady-state seepage. We started by recognizing that all motion is energy-driven. Therefore, the total energy was equal to the kinetic plus the potential plus the pressure. In most cases, the kinetic energy will be very small component, so the total energy will be the elevation-related energy, potential energy plus the pressure in the fluid. And if we divide by the weight, then we concluded that H total is equal to H elevation plus H pressure, where the pressure head, you can think of this P as pressure, or how much does water rise in a pipe, in a piezometer. So this is a good mental model to have. Whenever you are confused, just put in your mind a pipe at the location and estimate how high the water rises. That's the pressure, and indeed the fluid pressure that controls effective stress and the shear strength is going to be equal to H pressure times the unit weight of the fluid, in this case water. The next equation that we use for most studies where we need to understand the amount of flow and the flow rate and what will be the size of pumps, or at what rate are we going to lose water, is Darcy's equation, which tells us that is KIA, A being the apparent cross-sectional area, including the grains, I being the gradient, and I think that we made a compelling argument that the gradient that we have to use is the gradient of the total energy. This is the one that drives the flow, so this is dH total with respect to some length, is the total energy that drives the flow. And then by the time we assume that there was mass conservation and that there was no changes in saturation, no volume expansion in an element of soil, so that means that all the flow that goes in is equal to the flow out, we derive Laplace's equation that tells us that the second of the total energy, or the total head with respect to x twice, plus the second of the total head with respect to the z direction twice, is equal to 0. And so the procedure to solve all problems in seepage and a steady-state flow is basically always the same. Identify your boundary conditions, because we need to solve this differential equation. Next, solve Laplace. And once we know the total head everywhere in the region, xz, now we already know and we can measure the elevation at any point. And with the total head and the elevation at any point, now I can determine H pressure at any point, because H pressure is equal to H total minus H elevation. And if I know H pressure and know the pore pressure, and depending on boundary conditions, I can compute the effective stress, and then I can compute the tau ultimate, for example, for stability analysis. So this is always the sequence. And by the way, knowing the total head everywhere, I can compute the gradient everywhere. That means that I can compute the flow rate everywhere in my system. The issue is, how do we solve this equation? And there are many ways to do it, and there's some very simple boundary conditions and geometry. There may be a closed form solution, for example, for radial flow. Otherwise, we have to solve it nowadays numerically, but there is also a possibility that we can solve it graphically or with analogs. It may appear outdated, but today I would like to review with you the graphical solution. I think that every time we have a problem of steady-state seepage, we should do in the back of an envelope. Just take a page and sketch the problem and feel like a water molecule going from an inlet to the outlet. Draw those flow lines. Identify what are the inlet and the outlet conditions and the boundary conditions for flow, because that perception of the problem is critical for an engineer, but furthermore is critical to feed numerical solutions and to be able to rely on the outcome. So this is indeed probably the most critical starting point. What are the boundary conditions? So let's take a few cases. Let's start by clarifying one situation. If I have a swimming pool, it is hydrostatic, and so what is the distribution of the total energy in this system? Well, at any point, compared to a datum, I can check at any point what is the elevation of the point, and remember, we are going to put a piezometer to get the pressure head, and so we can place, at every point we can place a tube and think how high will the water rise in the tube. And because of communicating tubes, the water will rise in the tube as much as it is on the outside. Therefore, this will be the H elevation of the point, and this is the H pressure at the point. And the sum of these two is the total head at that point. Now I can go to the bottom of the swimming pool, and once again I place a tube, and by the same reasoning it will go to the top of the water, and this is the elevation. And you can readily convince yourself that in a swimming pool the total head is constant everywhere. This is a good one to remember. Let's take another case. Let's say that I put a big block of material interfering with the flow of water above the surface, and this is an aquitard at the bottom, so there is no flow across this lower level. So this is the water upstream, and let's say that there is a film of water downstream. Now, what are the boundary conditions? We have to realize that water will flow through the subsurface as through a pipe. And so the water is channeled between this concrete block. This is one boundary for the flow, and the bottom aquitard. So this wall here is the shortest flow line for any water droplet to go through. That would be the shortest flow line. And the longest flow line will start far away at infinite, will come along this interface, and will end all the way at infinite. So this is the longest flow line. For lack of colors, I consider this wavy line as the longest flow line. And all the flow, it doesn't matter where the water droplet enters the soil, all the flow will get constrained between these two boundaries, between the shortest flow line and the longest flow line. So these are two boundary conditions, the flow boundary conditions. What about the energy boundary conditions? Well, it is always good to think that feel as a water molecule. Where will this water molecule go? Well, this water molecule will go something like this. So this is the trajectory a water molecule will follow. So this is a flow line. And flow lines start at the first equipotential and end at the last equipotential. So if you can see, if you can feel where that water molecule will go and the trajectory that it will drive, you will recognize right away that this is the first equipotential total energy, and that this will be the last equipotential. the last one. And by the way, we know the energy on the first equipotential because I can take the bottom here as the datum from where I measure all the elevations. So I take a ruler and I measure this is the elevation, and I place here a pipe, and this is like a swimming pool. We already did the case of the swimming pool. So the water will rise to this elevation. Therefore, this elevation plus this H pressure gives me the total energy on that first equipotential. I can do the same with the last equipotential. This would be the H elevation at this point, and if I place a pipe, it will only rise to this water film. And so this elevation plus this H pressure gives me the total energy on the last equipotential. And that's what I know. I start with this energy, I will end with this energy level, and I will gradually lose that energy level from the inlet to the outlet. Please think, whenever you are confused about the problem, feel like a water molecule and draw the trajectory that that water molecule will describe. That is a flow line, and it starts at the first equipotential and ends at the last equipotential. So far, these are two examples. Let's erase the board and let's take other examples, because we need to be very confident in defining the boundary conditions in order to solve Laplace's equation, regardless of the approach that you are going to use to solve it. The next cases may be a little bit more confusing. One is a typical one that we find in books. So let's consider a plug, a soil plug. Here is a highly pervious stone, and this is another one. And we have here the soil plug subjected to pressure gradient imposed by two reservoirs at different elevations. So the water is coming from the top and is overflowing on the sides at the bottom. What are the boundary conditions in this case? Well, all seepage, hope is clear that water will be flowing down, then up the plug all the way into the reservoir on the right. All the seepage is constrained between these two flow boundaries. So clearly this will be one extreme flow line, and that is the other one. Now, what about the total head at the entry and the total head at the exit? In other words, what is the first and the last equipotential? If you feel like a water droplet and you put a color droplet here, it will draw a line parallel to the boundaries, the same one at the bottom. So it appears that all flow starts on this boundary, ends at that boundary. That gives you quite a good idea of what the first and the last equipotential will be. But if you are confused at any point, draw the datum. You measure heights with a ruler from that position. So let's say a point here, it has this elevation, and if I place a piezometer here, let's say that that is the piezometer, and I bring it all the way to the top, because of communicating tubes between this piezometer across the high permeability stone with this reservoir, the water will go up to the top of this pipe. And I can do the same for any other point here. It will have higher elevation, but the height on the piezometer will go to the same total elevation, and therefore this is indeed the first equipotential. And you can repeat the same, place a piezometer here, and it will go by communicating tubes to this elevation, and this is H elevation, and this is H piezometric head. And all across the boundary, it will remain constant. So these are my first and last equipotential, and these are the two extreme flow lines. It appears very weird example, but there are geometric situations underneath structures that we may actually have something that looks like this. Another situation is, imagine that we are pumping water, or it could be oil, from the subsurface, and we are far away from the boundary. We are pumping from this position, and imagine that we are far away, so we don't really have boundary effects. And so what is my first equipotential, my last equipotential, the boundary flow lines? It gets very tricky. But if you think as a water molecule, then you say, well, I will go from here to the location where I am pumping, where I'm pumping the water. And if I were here, well, I will do the same thing. And if I were a water molecule here, I will draw this flow line. So if these are all flow lines converging to the tip of the borehole, of the well, that means that this must be my last equipotential. But where are they coming from? Well, they're coming from a very large swimming pool. And remember that in a swimming pool, the total head is the same everywhere. So the far field, and it all depends how far you want to put it, the far field here is a far field of constant total head, which is controlled by the water here, because at any point, now forget about pumping, think of a swimming pool. At any point I can place here a piezometer, think how high the water will rise, and from a datum, this is the elevation, H elevation, and this is H piezometric. And so in the far field, everything has the same total energy, which is captured here. In the near field, the last equipotential where all the water goes to converge, it will be determined by how much you depressurize the well as you pump, not from the top, probably from a submersible pump. The last example that we're going to place in this small region of the board is another fairly common case in geotechnical engineering, where we have the phreatic surface, and the phreatic surface is not constrained. It can migrate up or down with the flow, and so that is a typical case of slopes, or the simpler situation would be to think of an earth dam. So let's assume that we mount an earth dam here, and this is a reservoir. So we can intuitively feel that the water will go in the dam, will migrate in the dam, and will create that surface. Now, inside the reservoir, like in any swimming pool, whether the bottom is flat or not, it doesn't matter. All this is an equipotential surface. Now, if I place a piezometer anywhere at the top of the phreatic line, it doesn't rise. That is it. So that means that at this point, the piezometric head on the phreatic surface is 0, and the total energy is controlled by the elevation. Therefore, I can identify at different elevations, I can go and intercept, and there will be one equipotential that will come here, one equipotential here, another one here, and so FlowNet will evolve to adjust the phreatic surface to make the whole system self-consistent with the boundary conditions while solving Laplace's equation. In summary, we are going to solve Laplace's equation by first of all identifying the boundary conditions. In the simplest of all cases, we would like to identify the shortest flow line, the longest flow line, and all the flow will be channeled in between these two. And if you are ever confused, put a drop of ink at some point in the system and see where it goes, because it will trace a flow line. And that flow line starts at the first equipotential and continues until it reaches the last equipotential. That will help you identify the boundary conditions right away. Now we are ready to proceed. For the graphical solution, there will be a couple of simple guidelines. So let's take the case of the block resting on the surface. This could be a cofferdam or some deformed shape of a water retention reservoir. And we are going to show some water on the upstream and the downstream to avoid issues with phreatic surfaces. If we feel like a water molecule and we put a drop of ink here, we realize that it's going to go down across the basement here and come all the way up. Therefore, this must be my first equipotential. That's my last equipotential. The shortest flow line gives me an idea of the first boundary to the channel where fluid is going to flow, and this is the longest one. This aquitard is going to create the lower boundary for flow. Now we're going to follow some very fundamental rules. One is that flow lines and equipotential lines, and they're always normal. It's like when you walk in a mountain and you see you follow the path that probably goats have described that tends to be horizontal and equipotential. Channels, erosion channels tend to be normal to it. That is the direction of the gradient, is the direction of flow. In order to simplify both the sketching of the flow net and the analysis of the flow net, we're going to create a net where flow lines and equipotential lines are going to intersect normally, but are going to describe quasi-squares. In other words, I should be able to circumscribe a circle, and the distance across and along the flow line should be pretty much the same, at least in the center of the element. So with those two very simple rules, now we can proceed, and once we have discovered the boundary conditions, we can proceed to draw the flow net. This part of the flow net, where we have this flat surface, it looks like a pipe. And so we can start probably doing a sketch here, and let's say that we're going to have only two channels, and far away from the boundaries, one flow line will be pretty much horizontal and equidistant, and because these two channels are going to carry the same flow rate. And so if we use the line of symmetry as one of the equipotentials, then in order to draw a square, I'm going to go ahead and draw the next two equipotentials. As I move further away, this is going to turn to go towards the last equipotential, so probably I can still fit another square, and it goes like that. And here is where the story begins getting trickier, because I still need to preserve the square shape. And so if this is going to be square, probably this is going to be something like that. By symmetry, we should satisfy the similar condition here. Folks, it takes just a few minutes to sketch a reasonable flow net. And of course, if you try to fit a circle here, you realize that this is not properly accomplished. So the easiest way to proceed is to put a transparent paper and fine-tune on a transparent paper and keep doing layering until the system is resolved. It is amazing how much insight you gain by drawing the flow net. For example, remember that gradient is dH dL. And as we will soon see, the gradient here at corners is going to be very high. And gradient gives you velocity, and velocity gives you Stokes drag force. So it's very easy to justify that there may be internal erosion near corners or at the bottom of cutoff walls. But above all, we see how the system and the flow evolves. Now, it may appear to be very arbitrary. How can you then start with 3 or 4 or 5 channels? Well, first of all, because this is just for demonstration purposes, but let me show you the analysis, and the analysis will help you understand that we didn't need much more complexity than the one that we have already obtained. So total energy that we're going to lose is this total head, because if this point has this elevation, and this pressure head, if you place here a piezometer, it will rise to the water in the swimming pool, which is the reservoir, and the total head at the exit is going to be this one, because this is the elevation and this is the pressure if I place here a piezometer. So the total energy that I have lost throughout the system is this one, the total head at the entry minus the total head at the exit. This is the L delta H. There are a couple of rules that will guide the analysis. Rule number 3 is that all channels carry the same flow rate. The other one is that the energy drop, the loss of equipotential between two successive equipotential lines, is the same for each of the drops. So that means that the energy lost between two consecutive drops is equal to the total energy lost between the inlet and the outlet divided by the number of drops. And in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 drops. So in this case, the number of drops is equal to 10, and the number of channels is equal to 2. So now let's derive the total flow rate, the total loss of water in this reservoir. The rate of loss of water is equal to the number of channels times the flow rate in each channel. Now, the flow rate in each channel is KIA, which is permeability. The gradient is the change in total head between two consecutive equipotentials divided this distance, I should have called this distance x, divided delta x. And this flow is happening across a height delta z times 1. In the perpendicular direction is 1 meter of length, so this is KIA. Now, because we impose the condition of these squares, that means that delta x and delta z are the same. So if we draw the flow net with this ratio, this becomes 1. And delta H between two successive equipotentials is the total energy loss divided the number of drops. So now I have that this is number of channels over the number of drops times K times delta H total. And this is the total flow rate beneath that concrete block. And this is why the net is very robust, because if I increase the number of channels, in order, for example, if I would have doubled the number of channels, in order to preserve this square ratio, I also have to double the number of drops. And so the ratio of number of channels over number of drops for a given geometry is constant. So this is not arbitrary. And once again, the concern is not so much to use it for actual calculations, which we can certainly do. The important thing here is the ability to visualize, to feel the flow, to get the right boundary conditions. One more observation, particularly if you are thinking about flow rate, the total change in energy is very well known because your problem gives it to you. This is the function of the geometry of the problem, and it's going to be very stable. So very limited uncertainty here, even if you do it with a flow net that you sketch in 2 minutes. No uncertainty here because this is a constraint of the engineering design. Now, here is the problem. This one varies in orders of magnitude with an uncertainty of plus or minus 1 order of magnitude. And so my uncertainty in the flow rate is not in drawing the flow net. So you can do this in a few minutes. The uncertainty is how are we going to select the hydraulic conductivity? And that is another topic to be covered later on. The final analysis that we are going to do from the point of view of determining the pore pressure for effective stress for strength, if you would like to determine the pore pressure anywhere, well, you know the total energy, you know how much energy you lost across one drop, so the pore pressure at this point will be equal to the total energy at that point. So the pore pressure at a certain point A will be the total energy at point A minus the elevation, which you go and you measure with a ruler, the elevation at point A times gamma water. And now you can compute the buoyancy effect, you can compute the effective stress, etc. Flow nets may sound like a problem from the 1930s and the 1940s, a Casagrande, typical Casagrande problem or approach. Actually, it is a very valuable approach to have as engineers.